Okay, students, welcome to video class 32. And in this session, we are going to study about the Bode plots for higher order factors. Okay. Now, so far we have considered a open loop transfer function of a closed loop system, open loop transfer function of a closed loop system as say k into 1 plus st1 into 1 plus st2 x into this is of the form 1 plus sta into 1 plus st b, and this is of s raised to n. So when you analyze each factors, we can say there is a constant factor. This is a factor which determines the type of the system. And there are two first order factors. Why first order? Because the order of the polynomial is 1. So this is going to be a first order terms. So far now how we have found out is by putting s is equal to j omega, will be getting the sinusoidal transfer function. So that will be k into 1 plus j omega t1 into 1 plus j omega t2 divided by j omega raised to n into 1 plus j omega ta 1 plus j omega tb. Okay, now we have already seen that this k by j omega n, actually j omega raised to n will actually determine the initial slope of the Bode plot. Okay, so this is usually found out to get the initial slope, and the slope is, we have studied the slope to be 20n logarithm of omega. This is actually the slope of this particular line. Okay, 20 log omega. And how will you find out this? We'll be finding out this slope by this slope will be touching the 0 dB line at omega is equal to k raised to 1 by n. And if n is equal to 1, the frequency at which it touches 0 dB will be equal to k, or it will be, if n is equal to 2, this will be root of k, and it goes on like that. Or if n is equal to 3, this will be cube root of k, and so on. So and that is a speciality of these two terms. Now we have also found out, we have also gone through a theoretical analysis of these two terms separately, and thereby we defined the corner frequency. Now what is the corner frequency of this? The corner frequency is 1 by t1 for this term. This will be 1 by ta. Now what is the relevance of this corner frequency? Now at this corner frequency, now till this corner frequency, this particular term will be having a 0 dB magnitude, and after this 1 by t1, this starts to increase at a 20 dB per decade. This is what we have studied. Now in this case what we studied is at ta, say let's till at 1 by ta, this will be having a 0 dB, and after this point it starts to decrease at minus 20 dB per decade. Okay, so this is what we have found out. And as I have told you, while doing this, I have told you this is not the exact Bode plot. This is an asymptotic, or this is an approximated Bode plot. Okay, I will explain why I told you like that. This is an approximated asymptotic Bode plot. But now this is having some sort of error. That's what we are going to find out now. Now let us start with this term. How will you find out the magnitude of this? Say consider this first order term 1 plus j omega t1. Right. Now the magnitude is, we know that the magnitude is 20 log root of 1 plus omega t1 the whole square. Right. Omega t1 the whole square. Right. Now what we have done is, Now how do you arrive at this conclusion that at 1 by t1, from 1 by t1 onwards, it starts to 0 t, starts to increase at a rate of plus 20 dB per decade? That we found out by two assumptions, right? So when omega t1 is much less than 1, that is for lower frequencies, when omega is low, omega t will also be a lower quantity. So at lower frequencies, what happens is you can ignore this omega t1. Omega t1 can be ignored, and this becomes the magnitude of this 1 plus j omega t1 becomes equal to 20 log 1, which is equal to 0 dB, right? Now for the case of omega t becomes much greater than 1. So during this time, what happens is omega t1 or omega t1 becomes much higher than 1. Then this becomes 20 log, you can say this is omega t1 the whole square, or this is equal to 40, sorry, it is equal to 20 log omega t1. And from this we have seen that for the variation of decade of this quantity, what happens is this increases as at 20 dB per decade. That's how we draw. Now how do you find out this point? This point is the point which is common to both this. So we have assumed that we have just found out that 20 log omega t1 is equal to 0. Okay, but so that this omega t1 becomes equal to 1, or omega is equal to 1 by t1. This is how we found out the corner frequency, or we named this frequency as the corner frequency. Okay, now the importance of this corner frequency is this: after the corner frequency only, this particular term comes into play, or this will be adding a 20 dB per decade to the initial Bode plot. Okay, now there is a problem with this, because we have assumed as, see, look at this, look at the two assumptions. The one assumption is omega t is much less than 1, omega t1 is much greater than 1. But we haven't considered when omega t1 is closer to 1. Okay, when it becomes closer to 1, or when it becomes omega t is equal to 1, omega t1 is equal to 1. So when any value, say for example 0.9, it is comparable with 1. So you cannot neglect that. If omega t1 becomes omega t1 square is equal to 0.9, you cannot neglect. So that won't fall under this category or under this category, because this is more closer to 1. So we have just ignored that while we discuss this. Now why I have discarded that, I will give you an example. If suppose omega t becomes equal to 1, right? That is at corner frequency. Omega t1 is equal to 1 means omega is equal to 1 by t1. What will be the magnitude of that? That is, when you find the log of 1 plus omega t1 the whole square, what is omega t1? Omega t1 is equal to 1, so it will be 20 log root 2, right? 20 log root 2, and you will be getting that as, okay, so this is equal to 3 dB, right? So that means there is an error. So what we draw at t1 is it is equal to 0. From 0 only we will be drawing this 20 dB. Actually what will happen is, say this particular point will be somewhere over here. It's not exactly here. Now since this 3 dB error is always allowed for any system, so that's why we haven't considered this error or this correction while we have done the first order terms in our previous examples. Now what is going to be its impact when the order increases? Let us see that. Okay, for that let us consider a higher order term, say 1 plus j omega t1 the whole square. Okay, now what is the magnitude of this? You know the magnitude is, in decibel, will be 20 log the magnitude of 1 plus j omega t1, right? This is the whole square, or this is equal to 40 log, right? The magnitude will be 1 plus omega t1 the whole square, right? And we know that what happens is we have now what we want to see is we want to see the effect of the magnitude when omega is closer to unity, okay, or this corner frequency, yeah, corner frequency is closer to, or omega t1, right, is closer to unity. So that is at omega is equal to 1 by t1. So when it becomes equal to this becomes 40 logarithm of, right, root of 2, right? So what happens is when you find out, you can see that this is 6 decibel. So what you found out is, as the order of the factor increases, as the order, so if I am, say, if I am finding out that of an nth value, you can see that this will be equal to 20 n. So this is 40, 20 into 2. So that means you can generalize this error as 20 logarithm of root 2, right? So this is the error. So as you can see that as n increases, this, the magnitude is no longer going to be 0, but instead of 0, this will be equal to 20. So 20 n log root 2. That means as n increases, this error, this is called as an error. Error becomes significant. You cannot plot that as a 0 dB at the corner frequency. But what we did so far was, if you are to plot this without considering this error, if you are to plot this, what you do is you assume that omega t1 is much less than 1. So we will say that this is equal to 0 dB, and for omega t1 is much greater than 1, we ignore this, so that, right, so that this become 40 log omega t1, and you say that this, after this omega t1, that is at 1 by t1, what happens is it increases at a rate of 40 dB per decade. But actually the graph, actually you can see that this starts at, so at 1 by t1, this is not 0 dB, this will be somewhere over here. So this is 6 dB as we found out. Now if it would have been 1 plus j omega t1 the whole cube, then it would have been, yeah, it would have been 20 into 3 or 3 times, okay, 3 times, that means it comes around 9 dB. So at 1 by t1 it would have been like this. So that means the values closer to this, closer to unity become significant as n increases. So you can also find out the point somewhere over here. So it will not be like this. So you must, what we do is omega t1 is considered to be 1, and omega t1 you must consider it as 0.5. Similarly, you must also find out the omega t1 at 2, that is twice this corner frequency, half this corner frequency, so that you will get the points corresponding to this as well as this. So as you substitute omega t1 to t, you can see that this becomes closer to this. Then after this, it will be following this asymptote. So that means the exact graph will be coming like this. This is what is called as the corrected LM plot, logarithmic magnitude plot. Okay, this plot is called as magnitude plot. Okay, so this is called as a corrected LM plot or corrected Bode plot. Okay, so while this one This one is actually the approximated asymptotic Bode plot. Okay, hope you understood this. And this is, so if you draw like this, you will say that this is actually a border plot after doing the correction. Okay, so in your question, if it is not asked, you can always follow this asymptotic border plot. Now, even if it is in the first order, sometimes question can be asked, obtain the border plot and do the necessary correction. So if there is a question like that, you need to plot this 3 dB as well. Even though I have told you that 3 dB error can be neglected, this has to be shown. So for that, you should get the values using these equations, right? Using the equation which we have derived here in this case, while in this case it is this equation. Using this equation, find out the values for omega t1 is equal to 1, omega t1 is equal to 0.5, omega t1 is equal to 2. So obtaining that, you can see that, okay, so you can you will be able to get some values. It won't be, so for these two cases we assumed that this was 0, but it was not 0, as we can find out from here. So obtain some points at 1, 0.5 and 2. So you will get 3 points, mark that points, and as you can see that as omega t1 increases or it becomes higher values, it will be almost following this asymptotic border plot. Okay, so there will be a variation around the corner frequency, and a border plot with such a correction is called as a corrected logarithmic magnitude plot. So if asked in the question, you are supposed to do that. So what is the procedure? So even if you are asked, first of all you will have to assume that even the near corner frequency at one, you will have to plot the asymptotic border plot first, and after drawing that, do the necessary correction. Okay, is it clear? So that's it. Okay, now here is a question for you. Let's do a question so that you will understand this correction thing. Okay, so a unity negative feedback system has an open loop transfer function gs k by s into s plus 2 the whole square. The first question was to obtain the asymptotic Bode plot. If the question is something like this, then you don't have to worry about the correction. You may just draw the asymptotic Bode plot. Asymptotic Bode plot itself means approximated Bode plot. So you don't need to do any correction. But if in the question, be it a first order factor, if the question, if it is asked something like this and make the necessary correction, means you need to make the correction at the corner frequencies as I have explained here. Okay, so for that, even for that, you need to, so even for necessary correction, the first step is obtain the approximated asymptotic Bode plot, and thereby you are asked to find out the gain margin and phase margin. Okay, assuming one more part is also there, assuming gain margin for k is equal to 4. So in the first part, you have been given with a constant k which is equal to 4. And the second question is to determine, in the second part you have this k, you are asked to find out the value of k if for the gain margin to be 6 dB, you are given with the gain margin 6 dB, and you are asked to find out the value of k and thereby find out the PM. So in the first question it was k is equal to 4. This is going to be some other k. So that means obviously if the gain increases, gain changes, maybe, a phase margin is not going to change anyway, but okay, we'll see that anyway. Okay, this is going to change anyway because gain crossover frequency will change. So the phase margin will change. And similarly, the third question is determine the value of k for PM to be 60 degree. That's another case. So anyway, let's not make things more complex. So first of all, let us consider the first question. That is, you are to obtain the asymptotic Bode plot by assuming k to be equal to 1. K is equal to 1. Okay, so let's see that. Okay, so when k is equal to when k is assumed to be 4, your gs becomes equal to 4 divided by s into s plus 2 the whole square, right? Now, if gs is equal to this is your open loop transfer function. Now, what you need is you need a sinusoidal transfer function. For that, what you need is put s is equal to j omega, right? Put s is equal to j omega, so that why there is no hs, because it is said that it is a unity negative feedback system. That means your h of s equal to 1. So putting s is equal to j omega, you can find out your g of j omega as 4 divided by j omega into j omega plus 2 the whole square, right? So that's it. So this is it, g of j omega. So this is what is called as a sinusoidal transfer function. Sinusoidal transfer function, right? Now this is actually your sinusoidal transfer function, right? Now you want to make it into a Bode form, right? So if you want to make it into Bode form, what you do is you must take this constant out. So this will be 4 into 4 j omega into 1 plus it will be 1 plus j omega by 2 the whole square, right? When you take 4 outside, you will get like this, right? It is 1 plus j omega by 2. So now this 4 and 4 get cancelled, so that this becomes 1 by j omega into 1 plus j omega by 2. So now what are the various factors that you can see? It is a very important thing that you should not. In the question, k is equal to 4. So you always have a tendency to take the value of the k equals 4. But the first thing that we require for plotting the Bode plot is you need to convert it into Bode form. So once when we convert into Bode form, we will, sometimes the constant may get cancelled as in this problem. So your new k value is 1. So in the Bode form, the value corresponding to this k is equal to 4 as in this transfer function will be equal to 1. Don't take that as 4. Okay, so the two terms will be, one is 1 by the constant term divided by j omega. We know that this decides the initial slope of the Bode plot, right? Initial slope of the Bode plot, right? Now so let us see, it is a type 1 system because it is s raised to 1. So this one is a type 1 system. Now for a type 1 system, this 1 by j omega passes through the 0 dB axis at omega is equal to the value of k. And what is your new k in the Bode form? That is k in the Bode form, right? That is what we need to find. It is not this k. Do remember, this is the k in this transfer function, but when it is converted to Bode form, your k becomes equal to 1. So that means this is equal to 1 radians per second. Okay, so till 1 radians per second, this 1 by the Bode plot starts. The Bode plot passes through the initial slope of the Bode plot passes through the 0 dB. That is, if you are to draw a graph like this, if this is 1 radians per second, you can expect a line passing through this 1 radians per second with the slope of minus 20 dB per decade. Why minus 20 dB per decade? This is because we have already studied in our previous video that this always offers a minus 20 dB per decade. Okay, minus 20 dB per decade. Okay, the only parameter that we understood is, we know that is it will definitely, it's going to pass the 0 dB at 1 radians per second. By this knowledge, you can plot the minus 20 dB line that passes through this 1 radians per second. Okay, now let's move on to the second term. What's in the second term? Second term is actually, so this is one is the first one. Second one is 1 by 1 plus the square, right? Square 1 by 1 plus j omega by 2 the whole square, right? So th this is it. So this is 1 by 1 plus j omega by 2 the whole square. Now, what is going to be this? Its magnitude. Its magnitude is, we know how to find out. That is, the magnitude will be equal to 20 logarithm of, okay, 1 by 1 plus j omega by 2 the whole square, right? So this you can bring to the numerator, and that is minus 2, so that this becomes minus 40 logarithm of 1 plus j omega by 2, right? Or this is equal to minus 40 log of root of 1 square plus omega by 2 the whole square. Okay, right? 1 square plus omega by 2 the whole square. Now the question is, so somewhere or other you need to find out this the value of this, right? Now we know that so as per our approximated prediction, what we do is, when we say, we know that this particular waveform will be having a 0 dB up to what, up to this omega t is equal to 1. Or what is this omega t? This omega t is, or here the omega t is actually omega by 2, or, right, or, isn't it? So omega 2, it is this is j omega t. So this is equal to, this is equal to 1, or the corner frequency becomes equal to what is the corner frequency then? Corner frequency is going to be 2 radians per second. So what you understood is, at 2 radians per second, this will be falling at minus 40 dB per decade. And it is at this corner frequency that we have studied a correction is to be made, because we know that at the corner frequency, since it is since the n is equal to 2, what is the error that can occur? This will be 20 into 2, or there will be a 6 dB error at the point. So we'll be plotting as asymptotic plot. We'll be plotting as if at corner frequency it is 0 dB, but it will be having a minus, yeah, it will be having a minus 6, because this is going to be minus n. So this I have drawn for the positive powers. Now if had it been 1 plus j omega t1 the all raised to minus n, then the slope will be the error will be minus 20 n log root 2, which is nothing but, in this case it will be minus 6 dB. So you need to plot that. So I will show you how to correct a Bode plot. Okay, so anyway, the corner frequency of this term is, how will you find out the corner frequency? This must be equated to 1, right? This part. So omega by 2 is equal to 1, or omega corner frequency is equal to 2. So that you will get this. Okay. Okay, now using these parameters, so we have identified the two terms, and using these parameters, you can, let us try to draw the asymptotic Bode plot. So the first step is just draw as we have drawn in the previous videos. So I'm considering a semi-log graph paper with a vertical axis as the magnitude in decibel. This is magnitude in decibel, and you need to write this scale. Okay, so you know how to write the scale. In the y-axis, one full division is 20 dB, so that means one smaller division is what? It will be 2 dB each, right? So you have 10 divisions, so one small division will be 2 dB each. So one full division is 20 decibel, that is in y-axis. And in the x-axis, now the question is how to set the x-axis. In the x-axis you have the decades. So you can select according to the frequencies that you have obtained. We know that the minimum frequency that we found out is 1 radians per second. That is, this particular initial slop passes through the origin 1 radians per second. That means you have Bode plot even before 1 radians per second. That means it should start a decade before 1 radians per second, right? So this is how you select this. So this axis, you need to consider this axis as 0.1. So what will be the next decade? Next decade will be 1, this one will be 10, and so on. Okay, so this is how it should be ascertained. Okay, so based on the, so first of all, the first step is to obtain the terms and its corresponding and frequency or the cardinal frequencies. This is called as a 0 dB frequency. In the case of plot, initial plot, you will be having the 0 dB frequency, and this is the cardinal frequency. Now you know how to find out the cardinal frequency, and not only that, this particular term will give you a minus 40 dB per decade, while this term will give you minus 20 dB per decade. So you must have a rough plot. Okay, rough plot in your paper itself, something like this. So it will be starting with the, so the graph will be going like this. So it will be having an initial slope of minus 20 dB per decade, and it will be meeting at 1 radians per second. And what is the corner frequency? The corner frequency is greater than 2 radians per second. That means this comes into play only at 2 radians per second, right? Now from this 2 radians per second, this term comes into play. So that means from this point onwards, this is having another slope. This won't be having a 20 dB. This will be having another slope, and this slope will be minus 60 dB per decade. Why? Because already this was having a minus 20 dB. Because of this factor, it offers another minus 40 dB per decade. So effectively, you will be having a minus 60 dB per decade. So you should have this this plot. That is an idea about the plot before plotting that in a semi-log graph paper. You should have an idea about how this graph looks like. So you must have a rough plot on your paper. Then you may transform that into a signal, into a semi-log graph paper. Now let us see how to plot this. So let's just explain and draw. So here we know that at 1 radians per second, this particular will be having a 20 dB. So you must so this is your 1 radians. So if you can draw a 20 decibel per decade line, it's very easy to draw that, right? Because we know that this is 20 dB, right? This is minus 20 dB, and this is this one of 1 radians per second, and this will be 10 radians per second. So this is a decade. So as one moves from this to this will be reaching from 0 dB, it will be reaching this point, meaning this is minus 20 dB per decade. So what is this line? What is this line? What is the slope of this line? Definitely this is, because as, do remember, one starts from this frequency, okay, this one, and that as one reaches to 10, this magnitude reduces from 0 dB to minus 20 dB. So that means this particular line is going to have a minus 20 dB per decade, right? So what I'm going to do is I'm going to draw this. Okay, so we know that this passes through 1 radians per second. Not only that, the corner frequency is higher than 1 radians per second. So you can plot this up to 2, right? So up to 2, you can make this dark lines. You can draw as dark lines. Okay. So this is the initial slope, and you may write this as 20. This is 20 decibel per decade. Okay, right? Now this will be extending up to what? Up to which point? Up to this point, right? So now we will have a dotted lines after that. Okay, so it goes on like that. So when you draw this, so you must be very careful in drawing the point. So, okay, so this is the point. This is the point corresponding to 2 radians per second. Okay, so just I am plotting this by a dotted lines like this. Okay. Now, from this point onwards, I have already found out that this must be a 60 dB per decade. Now, how will you draw a 60 dB per decade? Now, you can have a 60 dB per decade. Say, this is 1 decade, right? What is this line? What is this line? Say, you can do the same thing. I told you that it will be nice always to draw parallel lines. That will be more effective than finding out the decibel and decades and drawing the plot. Now, if you can draw a parallel line which passes through this is going to be having a slope of why this is called as 60 dB, because look at this. As one moves from, so at 0 dB, so at this 10 radians per second, this was 60 dB. Now when it reaches 100, this is 100, right? This one is 100. That is the next decade. As one passes to one decade, it reduces from 60 dB to 0. So that means the total slope over a decade is minus 60 dB per decade. There is a change of minus 60 dB per decade. Or you can, the same is this. Say, what about this line? Okay, this is also 60 dB per decade. That is, so it was 0 dB. As one moves from one decade, it reaches minus 60 dB, right? So if you can draw a parallel line, so you can use anything, you can use parallel line. So you can a parallel line similar to this. What I meant is, say if I can draw like this is going to be, so this line is going to be a parallel line to this or this. Okay, so I'll just draw using a set square and a scale. Okay, so keep the scale. So this is actually your 60 dB. Keep the scale like this and the set square. Okay, and move in such a way that make sure that your scale won't move. Okay, bring that to this point. So from this point, if you can draw a hard line or a dark line, that is your minus 60 dB. So you can see that, see, look at this. This is a parallel line and go to this side as well. This is also parallel, right? This is parallel to each other. So what is this? What is this signal? Oh, sorry. What is this? This slope will be minus 60 dB per decade, right? Okay, right. So this graph is called as the, this is what is called as the asymptotic okay, approximated asymptotic Bode plot. Okay, or the plot without any sort of corrections at the corner frequency. And we know that there is only one corner frequency, that is at 2 radians per second. This is 2 radians per second. Okay. Now we need to make the necessary correction. Now the question is how to make the necessary correction. Okay. Okay, to make the necessary correction, what you need to do is you need to use this expression, right? You need to use this expression, and in that expression, we say we put the omega to be 2 radians per second. Okay, so we have assumed that at 2 radians per second this was 0, but we are going to find out that when you put omega is equal to 2 radians, this is not going to be 2, this is not going to be 0, but it is going to be 6 dB. Okay, that already I have shown you how it comes. Now in order to plot that, we'll be getting only one point, right? Now in order to get the corrected point, we need to get some points below this 2 radians and above this 2 radians. Okay, so for that what I do is I will be finding the value not only for 2 radians, finding the value for omega is equal to 1 radians per second, 1 radians per second, and omega is omega for 4 radians per second. Okay, that is the double of this corner frequency and the half of this corner frequency, and you may just substitute in this value so that you will get this as, so what I am going to find out is I am going to substitute in this equation 1 plus omega by 2 the whole squared. What I do is omega is substituted here, so you are going to get the values. Okay, so the values are okay. So for the correction, what I did was I started with the corner frequency. Substituting corner frequency, I got this as minus 6 dB. What's the meaning of that? Say, look at this graph. This was actually at corner frequency, this was following a minus 20 dB per decade. And since we have assumed that at the corner frequency, this particular term is also having a 0 dB. But when you substituted this into this equation, we found out that this is minus 6 dB. So that means this point is plotted in particular term is having 0 dB. And why you have plotted here? Because this plot is already having a minus 20 dB per decade. Now from this point, since this is corresponding to the 0 dB of that of the second term, what you need to find out is you need to find the point corresponding to this 2 radians. From this you need to find out that how much dB? 6 dB. So we know that one division is 2 dB, so 2 and 3. So you have from this point you have noted that 3 dB. So this is your 3 dB point. Sorry, minus 6 dB point. Now you'll be, what I did is again I doubled the, made the half. So I found out this to be minus 3.876. That is at 1 radians per second. Now what was actually the this is 1 radians per second. So 1 radians per second, at 1 radians per second, this Bode plot is already having a minus 20 dB per decade. So from this you need to identify that point minus 3.876 dB. So minus 3.876, one unit is 2, so this is 4, so in between this is 3.86 dB. So you got a point here. Now we'll get one more point, which is omega is equal to 4 radians per second, that is 4 times. So the frequency after this 2 radians per second, so I found out to be minus 13.97. Now what is the situation at omega is equal to 4? Now this at omega is equal to 4, this particular this thing is already following a minus 60 dB per decade. Okay, this is already having a minus 60 dB per decade, right? Now but the amplitude suggests that this is minus 13.97. Now from where will you calculate this minus 13.7? That is at this 4 radians per second. See, if there would not have been a term, this term, then the graph would have gone like this. right? So this graph is already having a minus 20 dB per decade. Now at 4 radians per second, from this you need to count that 13 minus 13.97 or minus 14 dB. So I'll just do it for you. So this is actually the 4 radians line which touches over here. So from this the actual plot must be minus 13.9. So this is one division, 2, then 4, 6, 8, 10, 12. Okay, now you have the 13 point or almost 14. So this is the point. Okay, so this must be the point, right? So this is the point. 1, 2, 4, 6, 8, 10, 12, right? So this must be the point, right? So these are the 2 points we have identified. Now at 1 radians per second, okay, this also be found. Now it seems to be a bit far from this, so I have also taken one more point, that is 0.5 radians. So this was found out to be minus 1.03. Now at 1.5, what you need to understand is at 0.5, sorry, at 0.5 radians per second means this is the 0.5 radians per second. So at this point, this particular wave is already having a minus 20 dB per decade. Now from this point, you need to find out 1 means it is half of the 1 division, right? So it comes closer. So you got a point something like this. So you can freehandly draw connecting those points. Okay. So as the frequency increases, what happens? So this is actually the error, and the maximum error, you can see that the maximum error occurs at the corner frequency. So this is actually the corrected Bode plot, the colored plot. This is actually the corrected LM plot, logarithmic magnitude plot. Okay. Now this is actually the Bode form. Now next is we want to find out the phase angle. Now phase angle is simple, right? How to find out the phase angle? Phase angle is the phase of each terms. What is the phase of this term? This is 0. What is the phase of this? This is 90 degree. Okay, this one is 90. So this one is 0 degree, this one is 90 degree, right? What about this? This will be, you have two terms, that is 1 plus j omega by 2 into 1 plus j omega by 2. So you will be having this as, so when you, this is tan inverse omega by 2, right? But there is two terms, so that means when you add this, now what you do, what is the effective will be the numerator phase minus the denominator phase. So your phase will be 0 minus, that is 0 minus 90 degree, right? You have the 90 degree, then what else? Then is minus 90, right? Minus 90 minus tan inverse omega by 2. Okay, so it will be minus 90 minus tan inverse omega by 2. Again you have one more term, so you can say that this is 2 times tan inverse omega by 2, right? Okay, so this is like if you didn't understand, okay, this is just like this, j omega into 1 plus j omega by 2 into 1 plus j omega by 2. Okay, so there is a tan inverse omega by 2, there is another tan inverse omega by 2. When you add this together, it will be 2 tan inverse omega by 2. Okay, so this is minus 90 minus tan inverse omega by 2, and I'm going to have a tabular column with omega and the corresponding phase. Okay, right? Okay, so these are the points that I have got for zero point 0.1 omega. 5 is found out to be minus 95.7, 0.2 101.4, 0.5 minus 118, and 2 minus 180, and 5 226. So I'll just explain how to plot this phase. So this phase is to be plotted in this side. So okay, so this will be, this is, mark this as minus 180 degree. You must draw in such a way that minus 180 degree has to be in line with the 0 dB. So that means this is going to be, this division is going to be minus 150, this is minus 130, right? 130. Okay, so okay, so this will be 130, 110, right? Okay, so this is 120, this is 180 minus 150, 150 minus 30, 120, okay, minus 120, and this must be minus 90. Minus 90 plus 30 minus 120 plus 30, 150, 1 plus, okay, now this will be minus 210, right? Minus, okay, so this is minus 210, and this will be minus 240, and so on. Okay, so this is how you need to mark, right? And this is a simple graphical plot, so you may just draw that. The only thing is that you need to specify the scale somewhere over here, that is in the phase plot. One axis, the x-axis, is having a 30 degree division, right? The full division is 30 degree, so that means one division will be, you have 10 lines, so 3 degree each, right? So that's it. So using that, you will be getting that as getting the graph. So what I need to do is say at 0.1, so 0.1 radians is this, right? 0.1 radians is this one, 0.1 radians is this. At this 0.1 radians, it's having a 95.7. So we already know this is minus 90, this is minus 93, this is 96. So it will be coming somewhere over here. So this is the point at 0.1. And what about at 0.2? 0.2 will be this. If this is 0.1, then this must be 0.2. 0.2 comes around 101. So you can find out from by counting 3, each subdivision has 3 degree each. You can find out the exact point of 101 and all these things. So you may do it by yourself, so that you will get this as, so okay, look at this. So you will be getting a phase plot something like this, t degree. Now from this, the first step is to find out the GCF and PCF. Now what is this GCF and PCF? GCF is actually connected to this Bode plot, right? Now this GCF is actually the frequency, the frequency at which this plot crosses what? Crosses this the 0 dB axis. Okay, so when you consider the approximated plot, this will be 1 radians per second. Okay, so you can see that this is actually, this is the point at which the actual or the corrected LM magnitude plot goes. Actually, when you look at this the asymptotic plot, that will cross at 1 radians per second. Now if there is a correction, or if in the question if you are asked to correct this, then you should take the corrected Bode plot. Now looking at the corrected Bode plot, you can see that this Bode plot, this corrected Bode plot actually crosses at 9 radians per second. 0.9, sorry. So this 9 corresponds to what? This 9, since it is a point between 0.1 and 1 decade, this must represent 0.9 radians per second. So your GCF you found out to be 0.9 radians per second. This you should get from where? Very, very important, from the corrected Bode plot. Okay, corrected Bode plot. What about this? You don't need, I mean, it is very simple. From the tabular column itself, we understood what is PCF, and PCF is 2 radians per second. Okay, so from this, we understood what you understood is your GCF is 0.9, PCF is PC. So that means your GCF is, or your PCF is greater than GCF, or GCF is less than PCF. This is a, okay, we'll follow on. GCF is less than PCF, meaning this is a condition for a stable system. So this is a stable system. What is this gain margin now? Now how to get the gain margin? Now what is gain margin? Gain margin is actually the negative of the gain at gain at PCF. Now what is at PCF? What is your PCF? Gain at 2 radians per second. So you will have to find it out like this. So look at this graph. This is 2 radians per second, and you can plot this somewhere over here. So you can see that this is 12 radians per second, right? 1 2 3 4 5 6 6, right? So this is this is 6. Okay, so you can see that 6 into 2, 12 decibel. So this is minus 12 decibel, right? Negative of the magnitude that you get from the magnitude at PCF, that is GCF, right? So GF, that is gain margin. So gain margin is the magnitude or the gain at PCF, or we found out from the plot this as minus 12 dB, or which is equal to plus 12 dB. Okay, so if you are not using the corrected graph, so look at this, that also you can learn. If you are not using the corrected graph, what you are going to get is, see, 1 2 3, you will be getting that as 6 dB instead of 12 dB. So that's a significant change anyway. So that should not happen. So for a higher order system, what I suggest always is, for a higher order system, that is for the orders greater than or equal to 2, always do the corrections, because 3 dB, so up to 3 dB error it is permissible. So that means up to 1 degree you can just plot the asymptotic plot. But when you deal with higher order terms, that is the terms which are having orders greater than or equal to 2, you must do the correction at the corner frequency. Otherwise you will be getting a different answer for the, especially for the gain margin. So look at this. So instead of this, if you are using this asymptotic plot, you would have got this as 6 dB, which is 1/2 of the original gain margin. Okay, hope you understood. That is the importance of correcting the graph. So make it a point that for higher order, so I am writing it for you, this is very important, for higher order factors, that is for n greater than or equal to 2, correct the asymptotic Bode plot at the corner frequencies. Okay, this is very, very, very important. Okay, now if it is a single order, I mean first order terms, okay, then there is no need for that. And not only that, in the question, if it is not asked, it's not at all a problem. But for those factors which are greater than or equal to 2, even if it is not asked in the question, you must do the correction if you want to do the phase margin. And if it is not asked, you must tell these two things. From the graph, had it not been corrected, you would have got 6 dB, and since it is corrected, it will be 12 dB. Okay, so this is it. So that's the gain margin. Now what will be the phase margin? Phase margin is nothing but 180 plus the angle at GCF. Now the gain crossover frequency we found out to be 0.9 radians per second. Now what is its value at 0.9 radians per second? Okay, that's what we want to see. So when you mark this, this is your 0.9, right? This is your 0.9. So when you mark this, you will get somewhere over here. So this point corresponds to, this is actually corresponding to, minus 123 divisions, right? 123, 126, 29, 32, 32, then 35, 38, right? So it is minus 1, so it is 30 minus 138. So this corresponds to, so this corresponds to minus 138 degree, right? So that means you will be getting this as minus 180 minus 138 degree, or which is equal to 42 degree. So look at this. So gain margin is positive, phase margin is positive, and do remember, gain margin has to be taken with respect to the corrected Bode plot, not the asymptotic Bode plot. If the question is not asked, you must do this both the things and specify that from the corrected Bode plot it will be this gain margin, from the asymptotic Bode plot it will be this. So in this problem it will be 12 dB from a corrected one, and it will be 6 dB from the asymptotic or approximated Bode plot. Okay, so one more point that is to be noted is, as the frequencies goes away from this corner frequency, that is higher and lower, what we see is this Bode plot is approaching what? Approaching to the asymptote. And after a particular frequency, you can, now you may, if you keep on substituting higher values and very, very lower values, you can see that this is absolutely exactly equal to the asymptotic plot. So there will not be any too much error in that. But this error at the corner frequency is a significant one. You need to correct that. Okay. Okay, so the other two questions, that is these two questions, right? Question 2 and 3 we'll be doing in the next session. Okay, so far this is a very lengthy session, that's why I'm breaking it up. So we'll discuss that either in the live class or in the next video. Okay.